Today we're going to talk about rotational vibrational spectroscopy. Before we talk about what is rotational vibrational spectroscopy, what is spectroscopy? Well, spectroscopy is the study of absorption and emission of light. But when it comes to rotational vibrational spectroscopy, it can tell how the molecules interact. The rotational vibrational spectroscopy occurs in infrared region, and the molecule must be in a rigid position. The molecules such as CO2, HCl, or HBr can use these type of spectroscopy. Now you're looking at the HCl molecule spectrum of the rotational vibrational spectroscopy. So the first question is asking you to determine the spacings on the spectral lines. And we're going to determine the bone length using the spectrum provided below. So before we talk about, we determine the spacing on the spectral line using the math, we're going to talk a little bit about the spectrum. So if you look at the spectrum, the y-axis is absorbance, where x-axis is in wave number. Sometimes you can see a different type of x-axis, which I mean by it can be in frequency, which measure in hertz units, and it can be in energy, which measures in EV. And if you look at the spectrum, it can be in wave number, which measure in centimeter inverse. So it is very important you need to know the x-axis, like what type of x-axis is present in there, because sometimes the spectrum can be different. So before we answer the first question, let's label the branches if they're present. So there are three types of branches in the rotational vibrational spectroscopy, which is PQR. You can find the P branches on the left side of the spectrum. So if you look at this is the P branch. And you can mostly find the R branch on the right side of the spectrum, which is, this is R branch. So if you look at the black arrow down here, it actually showing the Q branch. So the Q branch are ideally taller than the P and R branch, but sometimes they can be missing. So currently, if you look at the spectrum, the Q branch is missing there. So only P and R branch are there. Put a K in here, but it's supposed to be BRANCH branch. Cannot spell. So yeah, they are transition, where a rotational transitions and the vibrational transition. So when it comes to P branch, we have a rotational quantum number, which is the change of J. So the change of J is equal to -1. For the Q branch, if they're present, usually their change of J is equal to 0. For the R branch, where their change of J, the rotational quantum number is +1. And for the vibrational transition changes, they represent the change of N. Usually their change of N is constant for all three branches, which is equal to +1. So now we talk about the branches. Okay, now we label the branches, and we also talk a little bit about the transition state changes. Now let's talk about the spacing on the spectral lines. So the very first step is to determine what is x-axis, because the x-axis can be in wave number, frequency, or energy. If the x-axis in wave number, the formula for the spacing is equal to 2b. If the spacings for the frequency, it's going to be 2cb. I'll tell you what b is in a moment. And energy, the spacing formula, is going to be 2hcb. Well, the b is a rotational constant. And okay, let me write it down. B is rotational constant. C is the light of speed constant, speed of light constant. and H is the Planck constant. So they all have a value in there. But however, when it comes to here, we're going to use the first one, the first formula in there, the wave number. So before we talk about looking at the spectrum, we need to determine the spacing between the spectrums. So the spectrums has the wave number value of 2600. It started with the 2600 if you look at it here. And then the second number is the 2700. But if you look at how many branches are apart from 2600 to 2700, there are 4 branches. And the difference between 2600 and 2700 is 100 centimeter. So we can divide that by 4 because there are 4 branches apart from those value. So if we divide it by 4, there are 27 centimeter inverse. I know that's not the exact spacing or estimation, but that's okay. That's the best I can do. So this is the spacing of the of the wave number, which is the 25 centimeter inverse. However, remember, it's very, very, very important. The units are in centimeter inverse. When we plug it into the formula, it is very, very important to be in meter inverse. We don't want that to be in a centimeter inverse. So we need to convert that 25 centimeter inverse into the meter inverse, which you will multiply with 100. It is very important you multiply with 100 because they are in inverse. So you will get 2500 meter inverse. Okay. So we have a formula, spacing is equal to 2b. So we have a spacing there. The spacing is 2500 meter inverse, which is equal to 2b, and we need to determine the rotational constant b. So we'll divide that by 2, and if we divide 2500, we got 1250 meter inverse. All right, so now we have a rotational constant. We need to find the formula. So what's the formula to determine the bond length? So let's go into next page. So we have that the rotational constant is at 1250 meter inverse. Let's introduce the formula to determine the bond length. The bond length stands for R. It represents the square root of H, which is the Planck constant, divided by 8 pi squared, the speed of light constant c, and then mu. And we have a different formula for the mu. I'll introduce in a bit, and then b, which is the rotational constant. So there's a formula for mu. Mu is actually the calculation of the atomic mass unit of the molecule. So the equation for the mu is m1 times m2 divided by m1 plus m2. Okay, the problem is given the mu in here, which is an AMU, which is 1.0078. So we can calculate the mu in here because the values are in here. So the mu is equal to 1.0078 times 34.9688 divided by 1.0078 plus 34.9688. So if we do that, we'll get we get 0.98 AMU. Well, we're not done that yet. We need to convert the AMU into the kilogram because we cannot put that into the formula because the units needs to be inconsistent. So, well, we get mu equal to 0.98 AMU, and we are going to use the conversion where 1 AMU is equal to 1.661 times 10 to the negative 27, making sure that this is given on the exam. So 1 AMU is equal to 1.661 times 10 to the negative 27. So if we multiply that with the AMU 0.98 AMU, we'll get 1.63 times 10 to the negative 27 kilogram for the HCl molecule. So now we got, okay, let's gather all the variables. So we have a Planck constant, which is H equal to 6.626 times 10 to the negative 34. And we have speed of light constant, which is equal to 3 times 10 to the 8. And the mu, it's basically the mass. We got 1.63 times 10 to the negative 27 kilogram. And then we have a rotational constant, which is the 1250 meter inverse. And now we're going to plug it into all the R value in there. So let me get 6.626 times 10 to the negative 34 divided by 8 pi square, 3 times 10 to the 8, times 1.63 times 10 to the negative 27. Rotational constant is going to be 1250. Okay, so let's calculate that. So if you put it in the calculator, make sure you put all together and make sure you close the parentheses so that you will get an accurate value. Okay, so after you find all the values and put into the formula, you should get the bond length equal to 1.17 times 10 to the negative 10 meter. Which is good because the bond length it has to be in 10 to the negative 10 meter. So if you get a different value than 10 to the negative 10, that means your calculation is wrong. So you can recheck and make sure you get the correct one. So yeah, if we go back to our problems again, we did talk about the spacing on the spectral lines. It is very important to know what is x-axis is. And then we determine the bond length using the spectrum. We already labeled the PQ branches. And the last question is asking, describe what occur physically to HCl for transition in the P branch. So in order to determine the transition, we need to understand what a gross selection rule means. So gross selection rule is for any transition to be possible. It actually tells what sort of molecule observed and molecule has a dipole moment. Because the dipole moment is very important when it comes to talk about the transition. So if you look at the P branch, the rotational quantum number, the change of J is equal to -1. So that means that HCl molecule will have an exact transition of a change of J equal to -1 during the rotational changes, and they will experience a dipole moment. But when it comes to vibrational changes, they will experience an exactation, because the vibrational changes of the transition is the change of n equal to +1 all throughout it. So yeah, thank you so much for watching.